Hi folks, we're going to take a look at number 5 from the last lesson of the unit. So here we've got a police cruiser approaching a right-angled intersection from the north, is chasing a speeding car that has turned the corner, is now moving east. Okay, and then they give us some information here, but let's draw the scenario first and let's see what we want to add to it. Okay, so I'm going to do is I'm going to use this point to represent the intersection, okay? And we've got a police car that's coming from the north, so towards this intersection, okay? And then we've got a car that's speeding and it just turned the corner, okay? So let's let that represent the motion of the car that's speeding, okay? So then it gives us some information. It says when the cruiser is 0.6 kilometers north of the intersection and the car is 0.8 kilometers east, the police determines that the distance between them and the car is increasing at 40 kilometers per hour. If the cruiser is moving at 80 kilometers an hour at that moment, what is the speed of the car? Okay. Now I'm not going to add any of this information to my diagram yet because these are all pieces of information at a particular moment in time. And we only want to incorporate that information once I've actually found my model and taken whatever derivative I have to take. Okay, so the question is what am I looking for? So I'm looking for the speed of the car. All right. So I'm definitely interested in this arrow here because this represents the distance the car moves. All right, now notice I'm talking about distance here because that's what I'm actually drawing on my diagram. And if I want the speed of the car, well, it's just going to be the derivative of this distance. Okay, in other words, the rate of change of the distance over time. That's what speed is. Okay, so I'm going to call this x since it's something horizontal distance. I'll call that x. But what I'm really interested in is dx dt. In other words, the derivative of this distance with respect to time. Okay. Now, if I look at the other information that I'm given, well, eventually I'm going to be given information about this distance, the police car's distance to the intersection. And the other thing I'm given is the distance between them at that particular point. Okay. So this tells me that because I'm working with these three lengths, I should be working with Pythagoras. So they told us it's a right angle intersection. So we know this is a right angle triangle. And because my information that I'm either interested in or given involves all three sides, I'm going to be using Pythagoras. Okay, so I'll call this distance here y, and I'll call this distance d, the distance between them. All right. So let's set up our model here. Well, very easy. I just have that x squared plus y squared is equal to d squared. Okay, now keep in mind here, I'm not looking for a maximum or minimum. We've had this set up before within an optimization question, but what I'm looking for here is the rate of change of x with respect to time. All right, so since I'm looking for the derivative of this expression here, I certainly could simplify and solve for x. I'm not going to do that because I'm able to derive this implicitly instead of using our derivative of an explicit function. I'm going to take the derivative implicitly. Okay, it'll make it a little nicer. So step one is to take the derivative with respect to both sides. Now here, I'm always going to use Leibniz notation because I want it to be really clear that I'm taking the derivative with respect to t for all of these expressions, because what I'm interested in and what I'm given is all information in terms of rates with respect to time. Okay, so this is my related rates equation now, and let's actually go ahead and take the derivative now. Okay, so what do we have? So derivative of x squared with respect to t, I have to apply the chain rule, so it's going to be 2x dx dt, okay, plus, again, I have to use the chain rule here, 2y dy dt, and then here, a third time, I'm going to have to use a chain rule, 2d dd dt. All right, so this is just my my related rates equation written in a simpler form. All right, so now let's hope that I have all the information in this equation other than dx dt, which is that thing we're looking for. Okay, so at the particular moment in time that we're interested in, do we have the distance that the car is from the intersection? And say here, yeah, the car is 0.8 kilometers east of the intersection. By the way, before I do this, we can divide both sides by 2. So let's make that easier. So x here at that moment in time is 0.8 kilometers. dx dt is that thing that I'm looking for, so I'm going to leave that unknown. Plus, y is the distance of the police car from the intersection, and at that moment in time, we know that it's 0.6 kilometers north, so 0.6. Okay, dy dt represents the rate of change of this distance. So this is where we have to be careful, because while the police car, is moving in that direction, what y represents is not the distance traveled by the police car, it's the distance between the police car and the intersection. And as the police car moves, this distance is decreasing. So it's not going to be 80 kilometers an hour, it's going to be negative 80 kilometers an hour. Okay, so make sure you're keeping in mind that if if an expression is decreasing, then its rate of change is going to be negative. Okay, let's go to the other side. The distance between them, well, we don't actually have the distance between them at that moment in time, but we can calculate it because, okay, we have this relationship between the 3 distances. So we know that at that moment in time, this is 0.6, this is 0.8. Now, if you kind of look at these numbers, remember there's a 3, 4, 5 triangle, which is a right angle triangle, or the 6, 8, 10 triangle. So if you used Pythagoras, you would see that this would be exactly 1 kilometer. So this is just 1. Normally, don't write that. And the distance between them is increasing at 40 kilometers an hour. So there's the 40. All right. So in the end, we were given all these pieces of information, or we're able to calculate it. All right. So now we can look for dx dt. Okay, so what is that? That's going to be 40. This is going to be plus 0.6 times 80, and all over 0.8. Okay, so let me find my calculator here, and let's calculate this. Okay, so we have 40 plus 0.6 times 80. Okay, and divide that by 0.8. And we get 110. Okay, so that means that the speed of the car is 110 kilometers per hour. All right, so let's recap here. Step number 1 was to get a good diagram to represent the situation. Once we had that, we realized that with the information given or of interest to us, Pythagoras was going to be what we were going to use to get our model. Okay, because it was an implicitly defined relation, we took the derivative implicitly in order to get our related rates equation. Then from there, we determine all the pieces of information needed to calculate the one that's our unknown. All right, that's it for this one.